When you really think about how far automation has come, it's absolutely mind-blowing. We've evolved from a world of clunky manual panels, where human operators were literally running around pulling levers and turning dials, to an era of systems that can actually think, adapt, and optimize completely on their own. Welcome to This Explainer. Today, we're tracing the incredible story of how industrial control technology evolved over time. We're going to dive deep into exactly how we made the leap from basic mechanical switches on factory floors to cognitive artificial intelligence managing massive global infrastructures. But before we jump back in time, let's just take a second to appreciate the sheer scale of modern tech. 5 trillion. That is a massive number. So what does it actually mean? Well, that represents the 5 terawatt hours of electricity that AI optimization can add to global wind energy production every single year. It is an almost unfathomable amount of power. And the craziest part? It's completely generated not by building bigger machines, but just by implementing smarter, self-learning control systems. But to really understand how we achieved this level of technological brilliance, we need to go back to where the story started.
Okay, let's dive into this. Section 1, the dawn of automation, from manual panels to PLCs.
So, before we had all these smart screens and iPads, manufacturing was an intensely physical, localized process. If you look at the 1950s, human operators literally ran physically between dispersed, localized control panels spread out across a massive plant. By the 1960s, we saw the birth of centralized control rooms. But here's the catch. These early centralized rooms were incredibly limited mechanically. They relied heavily on pneumatic signals, and manual outputs had to be transmitted all the way back to the plant floor. Sure, it gave operators a consolidated view, but it was still a rigid, hardware-heavy nightmare to maintain. The real turning point? That actually arrived in the automotive industry. Vehicle assembly lines required complex sequential logic, which initially meant using massive racks of mechanical relays and timers. We're talking a mechanic's worst nightmare and an electrician's bad dream all rolled into one. When things broke down, they were incredibly difficult to reconfigure and debug. Out of sheer frustration, the Programmable Logic Controller, or PLC, was born. PLCs allowed all those event-driven signals to be networked to a central area with electronic displays. It was an absolute game changer that spread like wildfire to water treatment plants, printing presses, and well beyond. Let's move to and see how this builds in Section 2, the automation pyramid, deconstructing modern control.
As manufacturing got more sophisticated, a highly structured hierarchy emerged to keep it all organized. We can actually deconstruct modern control into this classic 3-tier architecture, which is often called the automation pyramid. It's like a giant puzzle where raw physical data originates right at the bottom, moves up for processing, and eventually ends up at the supervisory computers at the top. That top level, supervisory control and data acquisition, or SCADA for short, provides the visualization and data gathering. This allows human operators to set parameters, while the lower levels just execute the logic in real time.
Now, if we zoom in on that foundational step, the field level, it helps to think of it in human terms. The sensors, they are the eyes and ears of the whole system, constantly measuring variables like temperature, pressure, and flow rate in real time. The actuators, on the other hand, are the hands. These are the mechanical devices, the valves, the robotic arms, and the hydraulic cylinders that actually do the physical heavy lifting based on the instructions they receive. Section 3. Eras of industrial flexibility. From rigid to integrated. Now, what's really interesting about this slide is seeing how having control is only half the battle. Over time, industries desperately needed manufacturing flexibility. We started with fixed automation, think early auto assembly, where changing the sequence was insanely costly and rigid. Then came programmable automation for batch processing, and later flexible automation, which allowed for rapid product switching with basically zero downtime. But look at that final leap to integrated automation. This is the real magic. This is where operational technology on the factory floor finally merged with enterprise IT networks, bringing us the true smart factories we see today. And this integration was made possible by an absolutely pivotal moment in software history. Back in 1993, the release of the IEC 1131 standard brought reusable, hardware-independent, object-oriented programming to industrial control systems. It was a massive deal. Suddenly, engineers weren't locked into these proprietary, inflexible operating systems anymore. Modern, powerful, multi-core industrial PCs running standardized languages could finally replace those older, closed-off systems. This drastically lowered hardware costs while massively boosting computing power. Section 4. Enter artificial intelligence, the cognitive era. So the crucial point is that even with super powerful PCs and perfectly structured code, traditional automation eventually hit a brick wall. Why? Because the physical world is messy. Data is chaotic, and strict rules just can't adapt to the unexpected. Traditional automation is fantastic at rule-based execution, but it totally fails when confronted with unstructured information. AI automation completely flips the paradigm. Using natural language processing and computer vision, AI can actually understand chaotic, real-world data. Whether that's extracting info from a messy HR resume, analyzing customer service emails, or hunting down complex IT security threats on a network, AI handles the cognitive decisions. This incredible capability gives rise to adaptive AI. As defined here, these are systems that utilize machine learning and reinforcement learning to continuously get better at their jobs without any human intervention. Reinforcement learning is particularly fascinating to me because it allows these systems to literally learn through trial and error by directly interacting with their environment. When they get feedback, they independently adjust their strategies to maximize the best outcome. No human handholding required whatsoever. And this takes us to the absolute cutting edge, agentic AI. These AI agents go way beyond just the factory floor. They can autonomously predict outcomes, make decisions, and take actions across incredibly complex enterprise systems. Think about everyday business. An AI agent can scan a massive pool of applicants to predict the best fit, while automated systems seamlessly schedule the interviews. Or in customer service and cybersecurity, the AI predicts the threat and the automation instantly isolates the compromised systems. It's this perfect, seamless partnership of cognitive decision-making and reliable execution.
Section 5. Intelligent Wind Energy, AI in Action.
Okay, let's tie this all together from those basic sensors all the way up to cognitive AI by looking at a really cool real-world case study. Modern wind energy is ridiculously complex. AI goes so far beyond simply turning a turbine on or off. During development, AI ingests vast amounts of historical climate data and geographic information to dictate the absolute perfect site selection, minimizing wake turbulence between turbines. In manufacturing, it optimizes the aerodynamic lift-to-drag ratio of the blades. And once it's up and running, predictive maintenance models use drone inspections to analyze vibration and temperature, detecting microscopic structural flaws in gear wear way before critical failure ever happens. And this brilliantly illustrates the whole culmination of our story. As this quote notes, we aren't throwing away the old rules, we are enhancing them. By mixing highly reliable rule-based logic with advanced machine learning, like fuzzy logic and neural networks, this hybrid control system keeps turbines operating flawlessly. It automatically tweaks things like rotor speed and blade pitch on the fly. It adapts to wildly varying wind speeds in real time, making absolutely sure we extract the maximum amount of energy possible from the environment. Which brings us right back full circle to why this technology matters so immensely. Remember that 5 terawatt-hour boost we talked about at the start of this explainer? To put that into perspective, that is enough clean electricity to power 1.7 million average homes every single year. Just by making our control systems smarter, we can literally power entire nations more efficiently. From running around with pneumatic tubes to creating intelligent, self-optimizing energy grids, the story of industrial control is nothing short of breathtaking. But it does leave us with a pretty profound question to ponder. As we transition into the Industry 5.0 factories of tomorrow, what exactly will our role be when the systems we dealt can finally think, adapt, and optimize entirely for themselves? Thank you so much for exploring this journey with me, and definitely keep questioning the future.